now we have understood about plane mirrors, spherical mirrors, and when I say spherical mirrors, we have concave and convex type. And these mirrors are of either converging or diverging nature. When I say converging or diverging, what I mean is when parallel rays come to the mirror, it may converge to a point that is known as focus, and that is of a converging nature. And if parallel rays come to the mirror and diverge and they don't meet at a point, but what I do is I deliberately do geometrical construction to make those rays meet at some point, and that is my kind of virtual focus because those rays are actually not meeting. So that is of a diverging type. Now what we have also found out is mirror formula and magnification in case of an extended object placed in front of a mirror. So the mirror formula is 1 by V plus 1 by U is equal to 1 upon F, where V and U are image and object distances respectively, and F is the focal length, and these measurements have to be taken from the pole. Any measurement in the direction of light travel or in the direction of the travel of light has to be positive and opposite negative. And essentially speaking, to the right of pole I have positive because obviously my ray of light would always travel from the left side of the pole, generally speaking. So U necessarily has to be positive in 99.9% of cases. There would be weird cases in which you could get U positive too. So U has to be negative in all the cases, 99% chances, but U is positive also when you would get some kind of weird arrangement of mirrors and lenses. We'll come to that later. Now V is dependent on two things: exact values of U and F, and we have done a big analysis on that. When V would be positive, when it would be negative, it depends on mod U and mod F values. And we've also calculated the magnification for extended objects. That magnification formula is minus V upon U. And we have also found out that this can be used for some applications of mirror, as in which mirror should be chosen for a beautician mirror or a dentist mirror, and which of the mirrors should be chosen for a rear view mirror. So that we have done already. Let's just take one small example and understand how do we use these two formulae. Let's suppose you have a concave mirror. Focal length of that concave mirror is 10 centimeter. See, when I say focal length, I am deliberately not providing you the exact sign convention value. You will have to figure out on your own, and no question would give you the sign convention values. You will have to use your head, as in which thing would be positive and which of the things would be negative, depending on which side of the pole it is measured. So focal length is of 10 centimeter. This is a concave mirror, and my object is kept 8 centimeter away from pole. This is your object. So where would the image be formed and what would be the nature of image? When I say nature, magnification and other things. So in this question, what you have to find out is image location. This is E. And nature of image. How do you find this out? I have to rescue this formula and this formula. Let's use them. If I have two approaches over here, one approach is the very basic approach, formula based. It would never leave you astray. The other approach is the ray diagram way. Even in the ray diagram way, I'll have to use a formula, but the ray diagram way gives me better understanding, a more apt visualization, but you don't never need it. But I'll just do it for the sake of completion to make you aware of these ideas. So if you have a concave mirror over here, All my assumptions are valid, right? Assumptions as small aperture of the mirror and paraxial rays. I won't mention those assumptions again and again because they have to be the basic criteria for all these measurements. This is your principal axis. The point where principal axis cuts the mirror is known as your pole. I'm 10 centimeter. As in, when I say I am 10 centimeter, the concave ray is speaking to you that I'm 10 centimeter focal length of a concave mirror. So the focal length over here, or rather the focus over here is capital F, and this measurement is 10 centimeter. But as this is to the left of pole, your F, small f, which is focal length, would be minus 10 centimeters. Now, I have kept the object 8 centimeter away from pole, which means it would be somewhat over here. This is my object. Let O be object. Now, I can have infinite number of rays, but the point is two rays should intersect to form an image or produce backwards deliberately, seem as they are coming out from one point. Let's find that out. One is your this ray. This would travel and reach the mirror normally. So this is normal incidence. Angle of incidence is 0 degree, so angle of reflection will also be 0 degree. So it would retrace its path. This is my first reflected ray. Let's take one more ray, like this. Now, this ray would definitely see that what is angle of incidence, and upon that it would decide its angle of reflection. If this is your F, I know that twice of F would be your center of curvature. So this essentially gives you the normal. So this angle is your angle of incidence, and at the very same value it would be getting reflected away. Do you think these two rays, these two guys over here, would ever intersect? Never, because they are diverging away from each other. As they would proceed forward, they would keep on diverging away. So you might have got the hint that these two rays would form a virtual image. How? By deliberate geometrical construction. Produce both of them backwards. They would intersect over here, and this is your eye. So without doing any calculation, I have got the idea that the image would be on the right side, which means V over here has to be of a positive value. Let's calculate it now. 1 by V plus 1 by U. What exactly is U? U is this thing, EO, which is 8 with a negative sign, because in the left hand side, minus 8. Whenever I write 8, you have to understand it's 8 centimeters equal to 1 upon F. What is F? Minus 10 centimeters. Now the calculation is not that difficult. What you'll get is 1 by 8, because this goes over that side, minus disappears, 1 upon 10. This gives you, don't worry about the LCM part, just multiply the denominators. Whenever you are confused of taking LCM, how much LCM would be, just multiply denominators. It's the easiest way out. 10 minus 8, invert it through. What you would get is 80 upon 2, which means 40. And when I say 40, it is 40 centimeters. So V is 40 centimeters, and this is your image location. And what would be the nature of image? For the nature of image, there's one small hint over here. This is a virtual image. So without doing any calculation, I can simply say it's a virtual image. So over here I'll write, for the nature part, this is the nature box, or rather the nature column. Virtual. And as there is a point object, so there would be a point image too. So there's no need of a magnification thing over here. But if I had an extended object over here of, let's say, 2 centimeters or 3 centimeters, I would have used this M formula to find out the magnification and the height of the image, and whether it would be inverted or not. If M comes out to be of a negative sign, it is inverted, and if m comes out to be a positive sign, it is erect. And generally speaking, erect image is of virtual nature and inverted is of a real type. So now we've understood all about spherical mirrors, and as we proceed on the illustration sections of this chapter, we'll understand more difficult and intricate problems. But let's jump on to refraction now, because we have dwelt a lot on reflection. Let's start refraction. What exactly is refraction? You might have some basic idea because you have studied in class 8, 9, 10 light, not in this way, but in some way. And if you recall the discussion on geometrical optics, or rather light, which we started, I gave an example or rather personal story, and I told you that we have to make this chapter interesting, no matter how boring this might appear to you. So that is our agenda all throughout this, and I don't think we have deviated away from that. So let's start the idea of refraction and let's give a different twist. So whenever you have an interface, this is interface, and this side of the interface is of a different medium, medium 1, and this side is medium 2. Obviously, if these two are different media, my speed of light would be different in both the media, and that would be dependent on the refractive indices of these two media with respect to vacuum. But let's keep that thought to a hold and proceed with the idea of refraction. We'll come to that sometime later. If I draw a perpendicular line over here, this becomes your normal. Now a ray of light reaching over here, like this is the incident ray, and this is your angle of incidence. If both the media were same, this ray would have proceeded undeviated, rather unrefracted. But it is not going to be the case over here. Dependent on the optical density, we'll come to it, what optical density is. Dependent on optical density, this ray over here could take this path or could take this path. This is towards the normal and this one is away from the normal. This is towards, when I say towards the normal, and this ray over here is away. When I say away, it is away from the normal. And when either of the situations would happen, this would happen when medium 2 is of a higher optical density corresponding to medium 1, and this would happen if medium 1 is of a rather the opposite way. I'm sorry. This would happen, normal would come, your refracted ray would come towards the normal when medium 2 is of a higher optical density than medium 1, and your refracted ray would bend away from the normal when medium 2 is of a lesser optical density than medium 1. And this optical density is somewhat related to my refractive indices. So let this value be mu2 over here and this be mu1 over here. And this mu1, mu2 values would decide how my angle of R, either this or this, would be dictated dependent on mu2, mu1 values. But before I do that, let's study laws of refraction, because that would give you an idea how exactly it's related to mu values. So the first law says sine of I upon sine value of R is equal to mu2 upon mu1, which in books you would find as mu of 2 with respect to 1. This is relative refractive index of the medium 2 with respect to 1, which we have touched upon in our initial discussion on geometrical optics when we were studying about the speed of light in different media. This is the form which you would find in books. Sin I upon sin r is equal to mu 2 with respect to 1. But the form which should be read by you or rather remembered by you is mu times sin theta is constant. Now what does this mean? Let's try to understand whether this can be correlated with this thing. Now sin I into mu 1, I'm just manipulating this thing. Mu 1 into sin I is equal to mu 2 into sin r. Now mu 1 into sin I, which means the mu value of here and the angle of this ray with the normal in this medium. Similarly, mu value in this medium and the angle of the ray in this medium with the normal, which means I can just generalize this thing over here. So this is the form which actually is more concise and easier to remember, but this would be more suited to solve questions. This won't be suited to solving a lot of questions. This would be applicable only in few questions, but this is the form which you have to always remember because this sums up everything about refraction. Now I have found out what would be the value of r dependent on I and mu values. But as we have studied reflection too, for the same value of r, I can draw infinite number of rays. So the second law puts a restriction on it. How? It says that the normal and incident ray and the refracted ray all lie, just guess, in the same plane. All lie in the same plane. And why is it important? Does it solve our problem? Yes, it does, because for the same value of r, I can have a lot of rays possible. But if I put them in the same plane, this thing comes over this plane, which means I have fixed my refracted ray. So if you can remember these two laws of refraction, you're through with refraction. Everything is based on these two ideas. Now, let's try to understand this one in more detail. The thing which you would be encountering is one of the media would be vacuum or air. Sometimes air is treated as vacuum and the refractive index is just treated as 1. So the speed of light in air or vacuum is treated as 3 into 10 to the power 8 meter per second. But actually that's not true, but we'll just take that thing for granted. And we can write it as a modified version. Sin I upon sin r is equal to mu of the medium. And when would this happen? When your situation is such that in the interface, this is your medium and this is your air or vacuum. Now, if I take different value of mu, as in if I change my mediums or rather media, I'll have different sin I upon sin r. My sin I won't change, my sin r would change, which means my sin r is dependent on mu values. So essentially speaking, either you would have an absolute kind of a calculation or a relative kind of calculation. In the relative calculation, you have to just keep in mind that I have to divide the refractive index of the first medium, and in the absolute situation, when the first medium is vacuum or air, there's no division done for the vacuum or air thing because the refractive index of vacuum or air is taken as 1. Now, all this is an introduction to refraction, and we'll proceed to a more difficult question or more difficult situation in the next course of our study.